Okay, we have just learned how to use integrals in order to compute the area between two curves. But another major use of integration involves calculating volume. And so in this lesson, we're going to learn how to calculate volume by cross sections. Now, what exactly is a cross section? Let's talk about that. I want you to imagine for just a moment a loaf of bread. I think everyone here can visualize what a loaf of bread looks like. Well, a cross section would simply be one slice of that loaf. So one slice of that bread. So what essentially we're going to do is we're going to have some sort of base that represents, let's say, the bottom of our loaf of bread. And on top of that base, we are going to build different shapes. We're going to build squares. We're going to build semicircles or rectangles or ellipses. And we are going to create a loaf of bread and calculate how much volume that we have in that particular loaf. So what we're going to be interested in doing is finding the volume of one slice of that bread, regardless of whatever shape it is, and then we are going to sum up an infinite number of those slices to get the volume. So perhaps a visual demonstration of this will be helpful at this time. Okay, here's an example of volume by cross sections. Let's say we have some curve, y equals x squared. That's a parabola. And let's say we have the line y equals 4. So that would be this horizontal line right here. And we have the left edge to be -2, x equals -2. So that's over here. And x equals +2. So we have this blue parabola as our base, and we'll think about that as the bottom of our loaf of bread. So on top of that, we want to build squares. And you notice that I have it set to squares. So this represents one representative square prism and out of an infinite number of these squares. So what we want to do is we want to find the volume of this one rectangular prism. So we can see that the volume is going to be the length, which is going to be the upper curve, y value, minus the y value of the lower curve. Okay, so hopefully that makes sense to you. This y value here is going to be some value, and this y value here is going to be some value. To get this distance here, you just simply take the bigger y value minus the smaller y value, and that's going to give you this length. Now, if it's a square, I know it doesn't look this way because it's not drawn to scale. If it's a square, then this side is going to be the same as that side because it's a square. And then this thickness is going to be dx, some thickness dx. So what you'll do is you'll find the volume of this, and then watch what we're going to do. We're going to use integration, and we are going to add up an infinite number of these squares. And as we do that, we are going to get the volume, because essentially this square is just one representative square. Okay, this is one representative square, and this square is just simply moving along the base of the solid at different places. And so we're just going to add up, once again, an infinite number of those squares. Now, it doesn't have to be a square. All right, it could be a semicircle. So let's go ahead and put that on there. It could be a semicircle. So there's a semicircle. So what we want to do in this particular case is we want to find the volume of this semicircle. So that means we need to find the area of the base, and you want to think of this as laying flat. So the base would simply be a semicircle. We know the formula for the area of a semicircle. And then the height would just be dx, all right? And that would give you the volume of this particular shape. And then once again, we want to take that shape and we want to add up, using calculus and integration, we want to add up an infinite number of those semicircles. And so that's what the idea of the volume by cross sections is all about. All right, to get our feet wet as far as finding the volume of cross sections is concerned, Let's take a look at two of the most common shapes that we're going to use to build this loaf of bread and build on top of our base. So the first is a square. And as I said before, let's just say that this is x. If it's a square, then this is going to be x as well, and this is going to be dx. So if the volume is length times width times height of a square prism, then this is simply going to be x squared times dx. Okay, now this one is a little bit more complicated. This is a semicircle, and it's a prism. So what you want to think about here is if I can find the area of the base of this, and I want you to imagine this prism laying flat. So I want you to think of the bottom of this prism being the semicircle and this laying flat. So we need to find the area of this semicircle. So the area of a semicircle is pi r squared divided by 2. Now here's the confusing part. X represents the diameter of this circle. We're not interested in the diameter, we're interested in the radius. So you need to take whatever this length x is, which is the diameter, and you need to divide it by 2 to get the radius. Then you need to square it because that's part of the formula. Then divide it by 2 because it's a semicircle. So let me review that. That's where it gets complicated. This 2 is because it's a semicircle. This 2 here is because it's radius and not diameter. So there's 2 divided by 2's in this problem. So let's go ahead and expand this. This is going to be x squared over 4, divided again by 2. So your final answer here is going to be pi x squared over 8. And that's going to be the way you find the area of a rectangular prism. But then if you want to make it volume, you just have to multiply it times the height, which is going to be dx. So the volume of this is going to be pi x squared over 8 times dx. And that makes it volume when you multiply by this thickness. Okay, example 2, we have, this is a calculator problem. And so the base of a solid is the region in the first quadrant enclosed by the parabola y equals negative x squared plus 4. We like these problems because you can use a calculator to do the integration. Each plane of the solid perpendicular to the x-axis is a square. Calculate the volume of the solid. Okay, so we're going to go through a few examples of this. And I have a 4-step process I want to introduce to you. Number 1, sketch the enclosed region R, which will act as the base of the solid. So y equals negative x squared plus 4 is an upside down parabola shifted up 4. So I'm going to draw that now. So it's going to be 1, oops, that's no good. Let's do it this way. 1, 2, 3, 4. All right, so this is going to be an upside down parabola. So there is, and we only want the first quadrant. All right, so that is our base. So maybe I'll kind of draw that in there. All right, so that's the base of our bread. Now, on top of that, we want to build a square. All right, so I'm going to draw one, I'm not the best artist here, but I'm going to draw one rectangular, or should I say one square prism. Okay, I'm going to draw one square prism here, and hopefully you get the idea. Our goal is to find the volume of this one square prism. And then when we do that, we're going to use calculus and we're going to sum up an infinite number of these. So if this is a square prism, all right, let's just label this point right here on the curve x, y. And that is a very important step right there. This point on this curve, on this yellow curve, this parabola, is going to be over some distance of x and up some distance y. So what letter represents the length of this square? It is y. All right, if it's a square, then what is this length also? Oh, it's also going to be y. So And what is the thickness of this particular prism? It's going to be dx. So it's going to be y squared dx is the volume. Now, you can't have the volume with two letters. So if it has a thickness of dx, then you need to have everything in terms of x's. So what is y? Oh, y is negative x squared plus 4. So I'm going to replace this with negative x squared plus 4. That's my y. I'm going to square that, all right, and then multiply that times dx in order to make it volume. And then I'm going to integrate this from when our region starts. That's going to be 0, all right, and it looks like it's going to end at 2, because if you plug 2 in here, 2 squared is 4, and 4 minus 4 is 0. So that's where this yellow curve hits the x-axis. So it's going to be 0 to 2. And at this point, we will let our calculator do the rest of the work. And when we do that, this is the answer that we get. 256 over 15. And once again, we like these problems because we can let the calculator do the most of the work. We just have to get the right setup. All right, example 3. We have the base of a solid in a region. Is the region in the first quadrant bounded by the x-axis, the y-axis, and the line x plus 2y equals 8? So maybe we need to solve this for y so that we can figure out what this line looks like. We'll put it in slope-intercept form so that we can easily graph it. So we'll have x plus 2y equals 8, and we will move the x to the other side, and then we'll divide everything by 2, and so we'll divide everything by 2. All right, so now we can see that this graph is going to have a y-intercept of 4 and a slope of negative 1/2. So let's go ahead and draw that out. So this is going to be 1, 2, 3, 4. And we can see that it's going to cross the x-axis when x is 8. 8 divided by 2 is 4. There's a negative in front of that, so 4 minus 4 is 0. So let me go ahead and draw those. 1, 2, 3, 4, 5, 6, 7, 8. All right, so this is a line, so we'll just connect these. All right, so that is our region in the first quadrant. That's the base. That's the bottom of our loaf of bread. Now, on top of that, it says we want to build cross sections that are perpendicular to the x-axis that are semicircles. All right, so now I'm going to draw a semicircle. Once again, I'm not the best at drawing these, but let's just see if I can do at least some sort of nice looking shape. All right, and so there is the semicircle. All right, and so let's just, once again, we're going to put this point on this curve, x, y. All right, so that's over some x and up some y. Now, remember the semicircle, we need to, the formula for the area of a semicircle is pi r squared divided by 2. All right, so the diameter of this particular semicircle is the letter y. That's the diameter. We need to divide that by 2. Now, y is defined as negative x plus 4. So, actually, you know what? Let's not skip that. Let's just do pi, and then we'll take y divided by 2, and we'll square it. And then we need to divide it by 2 because it is a semicircle. And then we need to multiply that by the thickness of this, which is going to be dx. All right, so what is y? We can't have y and x, so we need to put everything in terms of x. So y is defined as negative x over 2 plus 4. So it's going to be pi negative x over 2, all right, plus 4 divided by 2 squared divided by 2. Now, there's a lot of divided by 2's in here, okay? This divided by 2 is just part of the formula for the y. This divided by 2 is because we don't need the diameter of this circle. We need the radius of the circle. So that's why we had to divide it by 2. This divided by 2 is because it's not a whole circle, it's a semicircle. And we're going to take this and we're going to integrate from 0 to 8. So 0 to 8 dx. And once again, we have to be very careful to type this in our calculator properly. And if we do, we should get the answer 16 pi over 3. And for these problems, it's best to leave it as exact. So if you have a calculator that you can put in exact mode instead of approximate mode, that's the better answer. Okay, example 4. Now this is a more complicated problem. We have the volume of a solid whose base is bounded by the graphs of y equals x plus 1 and y equals x squared minus 1. So the first thing we want to do is we want to sketch both of those graphs. So here we have a linear function that has a y-intercept of 1, has a y-intercept of 1 and a slope of 1. So this is going to look like this. Just a basic linear function. All right, so then now we want to sketch the graph of this parabola. This is a parabola that's going to be going up, but it's going to be shifted down. So it's going to be shifted down, which is going to be the vertex. So the vertex will be here, and it's just going to be a basic parabola. So it's going to look like that. It's going to look like that. So you can see the region that, let's just go ahead and put red dots on the intersection points there. So this is the region that is going to serve as the base of our solid, the bottom of the loaf of bread. So we need to find the intersection between these curves, so that way we'll know our lower and our upper limit of integration. So let's go ahead and set these curves equal to each other. So x squared minus 1 equals x plus 1. I'm going to move everything to the other side, and that's going to give us x squared minus x minus 2 equals 0. And now we're going to factor x minus 2, x plus 1, and that's going to be x equals 2, and x equals negative 1. And so those are going to be our limits of integration. And so what we're going to do is we're going to do this same problem 3 different times. First, we're going to build squares, and then we're going to build rectangles that have a height of 1, and then we're going to build semicircles. So first, we want to build squares on top of this particular solid. And so we are going to, let's see if I can draw a good square here. Maybe I'll do it in blue. So this will be the bottom. This square is going to come out. So I'm going to try to draw it three-dimensional if I can. Okay, so there is our square. All right, so we need to find the volume of this square. Now, the length of this square is simply going to be the upper curve minus the lower curve. We've talked about that before. So the upper curve is the linear function. That's going to be x plus 1 minus the lower curve, which is going to be the parabola. So I'm going to take this minus and distribute it to both of these terms here. So that's going to make the x squared a negative, and that's going to make the negative 1 a positive 1. So essentially, that's going to be one side of our square. Now, it's a square, so that means this side will be the same as that side. So we need to take negative x squared plus x plus 2, and we want to square it. That's going to give us the area of this square. and then we multiply it by dx to get the volume. And then we want to integrate this from -1 to 2. And then we let our calculator do the work. And once we do that, we get the answer, 81/10. All right, now let's do this same exact problem, except this time we are going to use rectangles that have a height of 1. So it's going to be a similar looking shape. Okay, I'm going to draw this, and now it's going to be a rectangle, very similar looking shape, a rectangle with a length of 1. Okay, so this length, a height of 1. This length is going to be the same as the last problem. That's going to be the upper curve minus the lower curve. All right, so that's going to be the negative x squared plus x plus 2. Here's the only difference. The height of this rectangle is going to be 1. They tell you the height is going to be 1. In the previous problem, the height was the same as the length because it was a square. But in this problem, it's a rectangle, so they give you the height of 1. So I'm going to multiply that times 1. And then I'm going to multiply it by dx, which is the thickness of this particular rectangle. And then I'm going to integrate, because I want to get all the rectangles in this region, from -1 to 2. And once again, our calculator will give us 9/2. Okay, this time we're going to do the exact same problem, except now we're going to use semicircles. So this is the complicated one. I'm going to draw a semicircle. Oops, that's the best I can do there. And there's my semicircle. That's really bad, but I think you get the point. Okay, so the diameter of my semicircle is going to be the upper curve minus the lower curve. So that's going to be my diameter. So it's going to be negative x squared plus x plus 2. That's my diameter. But I need to divide that by 2 to make it a radius. And then I need to plug that into my formula for the area of a semicircle. So pi, and we'll call this, once again, we'll call this r, our radius, pi r squared. And it's a semicircle, so we need to divide it by 2. And we need to integrate from -1 to 2. And we need to multiply this by dx, which is the thickness of this particular solid. So this is going to make sure you have to make sure that you type this all in your calculator correctly. And when you do, you will get the following answer. 81 pi over 80. And that, my friends, is how you find the volume using cross sections.